we've got these 6 equations that we've derived, translational, rotational, and we can break them up further if you want. You can take the odd equations, you can take 1, 3, and 5, and say those are longitudinal. That's your longitudinal equation set. And what that means is that those odd equations of U and pitching moment and lift tend to describe the aircraft motion in its vertical plane. The vertical plane stays fixed. So I can lift in it, right? I can have drag in it, U, and I can rotate in it. So these tend to describe, the odd equations describe aircraft motion in its vertical plane. The even equations then are the lateral set. So 2, 4, 6 are the lateral equations of motion. And the lateral equations of motion describe the motion of the vertical plane itself. Lateral V, motion of the vertical plane, or I'm rotating the vertical plane, or I'm yawing the vertical plane. So when the vertical plane is moving, I use the lateral equation set. When I'm in the vertical plane, I use the longitudinal set. And the forces and moments for a conventional airplane tend to be independent, greatly simplifying a lot of analysis. So once we break these up into these forces, and we know that these are dimensional derivatives, we have to be able to get these dimensional derivatives given the stability coefficients. And the stability coefficients are non-dimensionalized using Q bar, S is the wing area, or the wetted wing area, and B for lateral motion is the wingspan. B is the wingspan. If you were in a longitudinal set, you would use the wing chord instead of the wingspan. So in the lateral equations, we use B, we use span to non-dimensionalize, and the longitudinal equation set, we use C, we use the chord to non-dimensionalize. And if you look back, you see that that's what we did. We'll do that again today. So, is everybody following that? If I were to take a perturbed delta L for this aircraft, then the moment arm, this aerodynamic center moment arm minus the center of gravity moment arm will give me a pivoting, but it'll be a negative torque since positive torque is counterclockwise. That's a clockwise torque. So I'll have delta M is minus delta L, XAC minus XCG. Now we're going to non-dimensionalize the moment. So we can non-dimensionalize the moment already. We saw that by going Q bar, S. Now we'll use the wing chord, C. Sometimes you see C bar, C or C bar. Then we'll have delta coefficient of moment, where this guy now is a stability coefficient, dimensionless. So the difference between a stability derivative, M, and a stability coefficient is that the coefficient has no dimensions. It's a unitless number. And on the other side, this guy is going to have delta L. Well, that's going to be minus, same Q bar, S, and then delta L. So this is going to be delta CL, coefficient of lift. They're going to cancel, yeah. These guys are going to cancel on both sides. So that's going to give me my net formula is going to be delta Cm. And what happened to the C? Well, I'm going to bring the C over to the aerodynamic center and normalize those lengths into percents. So this is going to become equal to x bar AC minus x bar CG. What's the bottom line? What's really important? This is equal to what we call the static margin, SM, KSM. KSM, we're going to be talking about it all week. KSM is the static margin. It's positive when the aerodynamic center is behind the center of gravity. When the aerodynamic center is behind the center of gravity, I have a positive KSM, and I have a negative delta Cm over delta CL. Well, is there an easier way to look at this? Yeah, I can divide both these by delta alpha. And if I divide both of these by delta alpha, then that'll give me minus, and that's the fundamental this is the fundamental equation of longitudinal static stability. Longitudinal static stability is that equation. So what does Cm alpha have to be to make a positive static margin? This is the lift curve slope, right? CL alpha? CL alpha is the lift curve slope. So, and its slope is always positive, a little less than 2 pi probably. So if this number is always positive, what can I say about Cm alpha for a stable airplane? Has to be negative, doesn't it? So your Cm alpha has to be negative. So when you look in the books and they give you Cm alpha, stable airplane. Trouble, probably a misprint. Okay, because you want the. So what kind of values do you want for design? Normally you want positive static stability, probably 3% to, I'd say, 8%, somewhere in there. If you have zero static margin, then the airplane doesn't care what angle of attack it's at, and you could have a dangerous situation in the cockpit. So I'm going to show you how to flight test for this stuff. To find out what my neutral point is. If, well, I can compute the center of gravity. I got a chart. Can I erase this? From NASA. This is NASA. If I pull back on the stick in the cockpit, what's going to happen? This thing is going to hold, that's going to go up, and the tail's going to lose lift, and the airplane will climb. If I pull back. And the positive delta E, by convention, causes a nose down of the aircraft. Let's suppose I could measure C sub L versus elevator deflection at different CG locations. So we know stability, this is going to be, say, -0.1, -0.2, and I'll have C. How do I get C sub L? Q bar S equals lift equals weight, and I know that, right? So I can say C sub L equals my weight over my wing area, which I know that for the airplane, divided by Q bar. So if I know my velocity from the cockpit, density, altitude, I know my weight, I know the wing area, I can get my C sub L as a function of velocity in the cockpit. So if I can do that, I go and I fly and I put the CG way forward. Right? I load up with fuel at, say, 2 different C sub L. So I'll fly at 1 C sub L over here, and I'll fly at 1 C sub L. When I pull back harder on the stick, I'll pull back harder on the stick, and I'll have another C sub L. It's slower. So this is slower velocity. Since it's the numerator, the faster the velocity, the smaller C sub L gets. So this is slow, this will be slow, and this will be fast. So I tested at 2 different velocities. I get 2 different elevator deflections, and I draw a slope. And this is going to be for a X forward, and we'll say it's 40% forward. We don't know what that means right now, but it's forward, 40%. It's way forward. Fine. Then we come and land. I burn out all the gas. So this is going to be for X aft. And we'll say that that's 10%. 10% aft. So I got 2 different afts. So I got 2 different slopes. Now I can take the slopes, which are delta E over delta C sub L, and I can plot them versus the CG position. So I know the CG position, say it's 0.1, 0.2, 0.3. I know what it was when I flew. So I just take those 2 slopes, and then this is going to be the forward slope. And my aft slope is going to be less. That's going to be my aft slope. And I draw a line, and guess what? Where that line hits 0 is my neutral point. Now what if you couldn't measure this? Could you use something else? Yeah, I could actually use stick force. So an alternative method, an alternate way, would be to measure stick force in the cockpit. And once again, now this time you're going to go versus velocity. And if you move the CG forward, delta Fs over delta true velocity, and I'll get a very similar looking curve for XCG. So you got 2 different ways you can do it. Now you'd have to have a stick force gauge in the cockpit, so you get one of those meat thermometers or pound gauges, and you pull back on the stick and you pull back harder, and you measure the force, look at your velocity, make those 4 points, and plot them. So for tomorrow, we're gonna plot these equations. So for tomorrow, we're gonna have a lift equation, CL0. We'll call this equation 1 or equation 2. And these are stability coefficients. So these are stab coefficients. You get those out of the table. You get those out of the book. So here's what I want you to do for tomorrow. I want you to solve 1. So solve this for alpha 1, sub it in 2, and then get, why am I asking you to do it? Because every year I do it, it takes 15 minutes, and you forget it anyway. So what I'm asking you, what is CM0 bar, or CM0 lift? What is it? What is that? And what does Ksm come out to be? What does that come out to be equal to? And what is Cm delta E bar? So these are called pseudo stability coefficients. They're called pseudo because they're functions of stability coefficients. You won't find these in the table. You won't find them in Nelson or in Roston. You'll find the stability coefficients, but you won't find these. You'll have to solve for these. And these are what we're going to plot.